Welcome everyone. In this video I'm going to continue my CH32 tutorial series, and in this video I'm going to discuss the SPI protocol. In the earlier videos I have already talked about GPIO handling, AD converter, I2C and timers and so on. And in this video I'm going to focus on the SPI, which is another communication protocol which I haven't introduced yet. In order to be able to demonstrate the SPI communication, I will use a sensor, which is the ADXL345 3-axis accelerometer. That's what you can see right here. And I have already wired it up according to the 4-wire SPI protocol, which means that we have a chip select, a MOSI, a MISO, and an SCLK pin connected between the two devices. And as usual, I use the CH32V003F4P6 microcontroller, which you can see here. And then I'm using the debugger module, which is on the left side of the screen, right here. And that's all. So I will use that to program the microcontroller through the SWIO pin. And I will use the USB to UART converter capability of this module and communicate with the microcontroller via USART. And basically that's all. And as usual, I'm going to implement the software in WCH's own environment, which is the Mound River Studio. And as you can see, I'm using the version 2 now, because previously I've been using the version 1, but I updated to version 2. And so far I can only say good things about it. It's very good. And you will see it in action how it works. So as usual, we have to start a new project. And then we get a bunch of microcontrollers, but we have the V003. So I select that, and I have F4P6. And then I just give some name to this project. So it will be Demo 10 SPI. And I just save it to my usual workspace and create the project. So since this is a new IDE in terms of looks, we can see that the project browser is here on the left side, and we already have the folder structure. And we have to know that we have to go under the user folder to get the main.c file, which is our important file, because that's the source file. So this file will be the one that we are going to edit. The example file is same as usual. So this is a pre-written code by the manufacturer of this chip or by the developer of the environment. And this is just a simple USART communication between the chip and the computer. And I'm going to keep few of these things, but as usual, I clean up a little bit. But before that, I also enlarge the fonts. So hopefully you will see everything well. So I don't need this thing here. I don't need this variable. I keep these. And then I clean up here a bit so we can see more things in a more clear way. So something like this. I'm not going to explain the USART because I have a dedicated video for that, so please check it. I just leave it as is because this is perfect for what we need it for. Maybe one thing I can talk about is that the USART pins are under the pin 5 and pin 6 pins. Pin 5 is the TX pin and pin 6 is the RX pin, and they are defined under GPIO-D. So the pins that I'm going to use is PD5 and PD6. And if we look at our configuration here, actually we can see that there are two wires connected to PD6 and PD5. One is this dark one and the other is the yellow one, and they go to the debugger, and then they are connected to the corresponding pins, TX and RX. And just as a reminder, the TX that comes out from the microcontroller has to go to the RX of the debugger, and then similarly the RX that comes out from the microcontroller has to go to the TX of the debugger. So before starting to develop the code, we need to familiarize ourselves with the chip itself that we are going to use for this demonstration. And as I said, this is the ADXL345 3-axis accelerometer. So the main features are listed on the front page. And what is very important is that this communicates via SPI or even I2C. And I could use the I2C with my already developed code for I2C, but since I want to demonstrate the SPI, I will use the SPI approach. And also within the SPI there are like two protocols. One is the 3-wire and 4-wire SPI, and I'm going to use the 4-wire SPI to show the full potential. And the advantage of the SPI over the I2C interface is first of all the speed. The SPI allows much higher speeds than the I2C. And then one fundamental difference between these two protocols is that the SPI is a full duplex communication, and the I2C is just a half duplex communication. And what this means is that the SPI can do simultaneous two-way communication, and the I2C can only do not simultaneous two-way communication. So both can talk both ways, but with SPI you can do it simultaneously, and that is a big advantage. And also, if we still want to compare these two protocols, a big difference is that for SPI you can select your chip by using the chip select pin on the slave device. But with I2C you can encounter a problem where similar devices have similar addresses. For example, displays, they typically have the same address and you cannot really change their addresses. So if you want to use one microcontroller with one I2C bus and let's say 10 identical displays, you cannot really do it in an easy way. You will need an I2C multiplexer because there will be an address conflict on the bus and you won't be able to distinguish between the devices. So that's, I think it's a big advantage of the SPI, that it's just a wire, which is the chip select port or pin, and that allows you to select between your devices. And if you want to know more about the protocol itself regarding the SPI communication between the chip and the microcontroller, of course you can read the datasheet, so it talks a lot about the serial communication and so on. I will just highlight the details as I write the code. But of course, it's up to you if you want to know more about how this chip works. So please study the datasheet thoroughly, and then you will be able to write your code for the chip. So coming back to the code, we have the USART already initialized and already implemented, but there's nothing going on with the SPI. So let's start with that. So I created this initialize function for the SPI. And before I forget, I immediately call this in the, let's call it setup part of the code. So then our work will be easier when we program this microcontroller. So what we need to do is that we create the structures, one for the GPIO and of course one for the SPI. And then we need to enable the corresponding clocks, one for the SPI and one for the GPIO, and we enable it. And I just remove this comma from here and it should be fine. And now we can start filling in the init structure for the GPIO, and that will basically mean that we assign the pins and their functions to the 4 SPI pins. So we start with the chip select. And then we have to first tell which pin we want to use. And that will be on PC4. So GPIO pin and 4. And then we need the mode. And that has to be output push-pull. And I tell you exactly why. So it's output because we have to toggle this, and it's push-pull because we are going to toggle it. So that's what push-pull means in this context. And then we have to set the speed. And then I just put it to 50 megahertz. It can be lower as well. I think it won't do anything, so it's fine. And then we initialize this, and we put this on the GPIO-C port. And we pass this structure here, and then it's done. And based on the communication requirements of the chip select pin has to be high by default. So we immediately pull it high here. And that is done by writing the bit of this specific pin. And we have the GPIO-C port. We have pin 4. And the bit has to be set, which means that PC4 is high. So something like this. And then I can copy paste this block here, more precisely this block, and do it like this. And then the next pins will be pin 5 and pin 6. So I just do them together. And then PC5, that is the SC-RK, so the clock. And PC6 is the MOSI, or sometimes SDA pin. So I can declare them together because they will have the same function when it comes to mode. So I use AF because they are now not GPIO pins, but SPI pins. So I have to use the alternative function. And then they will be push-pull because the master, the microcontroller, drives them, so toggles them, and the microcontroller has to toggle these two pins. So that's that. And then I paste this block again, but then we use the leftover pin, which is pin 7 on the same port, and this will be MISO, so master in, slave out, and then this has to be set into input, and it has to be floating because master in, slave out, so this pin must be toggled by the slave. Therefore it has to be a floating input, so the slave will drive its level up or down. And then I have to remove the speed because it's not relevant here, so it will look like this. And then we move to the SPI part, so that will be like this. And I just copy this because we will need it several times. So first we need the direction, but the order is not necessarily mandatory here, but I just want to define this first. So here the direction has to be 2 lines and full duplex, as we discussed this earlier. And then we need the SPI mode, which will be master mode because the microcontroller is the master. And then we have a data size, which will be 8 bits. Sometimes you can use the 16 bits, it depends on what kind of chip you are communicating with and so on, but here we use 8 bits. The registers of the 3-axis accelerometer are also 8-bit. And then one of the most important thing is the polarity of the clock, and this will be set to high. So the clock is high, so the idle level of the clock is high. There's nothing to explain here, but again, you have to always check the datasheet of your specific peripheral that you use. In this case, it's the datasheet of the accelerometer, and that suggests that it has to be like this. And then we have the phase, of course. So that is SPI CPHA, and that has to be this one, which means that the second clock edge is used to sample and shift the data. And that is when the second clock edge goes from low to high. And this is again to fulfill the requirements of the accelerometer. Then another fun thing that we have to set is this, and this is the chip select pin. So this has to be software driven, which is done by this. And this means that we have to manually take care of the chip select pin, but in exchange for that, we can assign it to any pins, which is very good. Then we have to assign a speed. And I just set it to 32, and this divides the main clock 48 megahertz by 32, so we will get 1.5 megahertz bus speed here, which is enough. And then we have to have the first bit, so this is basically the bit order if I'm not wrong, and we just set it to MSB because again the chip that we are communicating with requires this, so MSB first, let's say, protocol. And then we have to finally initialize this. So this will be SPI 1. The microcontroller has only one SPI. And then we pass this structure and done. But we also have to start the SPI. So that will look like this. And then we enable the SPI 1. And it's done, hopefully. And hopefully it doesn't have any mistakes. So I just see if it compiles. And it compiles. So far so good. So now we have the SPI bus working, and basically this, what we implemented here, would be equivalent on Arduino, for example, with the code under the hood, which happens when you call the SPI.begin line. So this is what would happen when we initialize the SPI. So this looks like this, but this is kind of equivalent to the SPI.begin. But we need the transfer as well. So now we can communicate via the SPI bus, but we don't know how. So I create a function for that. So this will be our function. And you can see that this has a return type, let's say, and that is a byte or an unsigned integer declared on 8 bits. So that's that. And why it has like this return type? Because it's two-way communication. So we send something to the SPI, and the SPI device that we are communicating with will respond with something, and we want to return that response. So first of all, we have to send data, and that is done with this. So SPI underscore I2S underscore send data. And then we need to use the SPI 1 bus, of course. And then we pass the data that we passed as a parameter here. So far so good. And then we have to wait until this byte is transferred outwards. So while this flag, which is on the SPI 1, and which is the transfer buffer empty flag, is reset, so it's not set yet. So this is how we wait until it gets transferred out. And then we have to wait again, but now instead of having this TXE, we have to check the receive buffer. So we send out the data and we wait until it's sent out. And then we know that the receiver, which is the accelerometer, will send back something. So we have to wait until it's sent back. So wait until the data is in the buffer. And then we can return with this SPI underscore I2S underscore receive data from SPI1. And that's all. So this is our like SPI transfer function. So I see if this compiles, and it compiles. So far so good, and hopefully I haven't done any mistakes. So now the next step is that we have to be able to read and write the registers on the accelerometer. And first let's implement the function that writes this register on the chip. So our function will look like this. It will have two parameters, a register address and register value. Both are represented on 1 byte. And as I said, now we have to take care of the chip select manually, because here we said that we have a software chip select and not hardware, so that means that we have to set the pin ourselves. And whenever we want to communicate with the accelerometer, we have to set this to another status, and the other status in the beginning is that the chip select has to be pulled low. So we have to write the corresponding bit. It's on the C port, it's the GPIO pin 4, and since it has to go low, then we have to set it to reset. So chip select goes low, and then we have our nice SPI transfer function, and we first pass the register address to it, so then the chip knows which register we want to modify, and then we can eventually pass the data to it like this. And once this is done, I can just do it like this. Then I can pull the chip select high, and basically that's that. So I try to compile this, and it compiled without any warnings or any problems. You can see everything is empty, so that's nice. And now comes the trickier function, which is the read register. So this is the function. Now this has 3 parameters: register address, number of bytes, and then there's pointer to the buffer. And this buffer will be the buffer which will be filled up with the values that are returned from the register. So therefore this buffer has to be implemented. So we jump to the top of the code, and we have the global variables here. So this will be again an unsigned int on 8 bits, and I just simply call it buffer. And then let's say 10 bytes will be stored in this buffer. It's more than enough, because in this example, the maximum number of bytes that we are going to transfer is 6. So this is enough. So then coming back to the code, I have to show something interesting here. So then when we look at the timing chart of the SPI communication of the accelerometer, we see this, but this actually tells us a little or a lot about how the data is expected. And what you can see here is that, of course, as we had to do it, chip select goes low, and then we start the clocking, and then we have the least significant bit here on the left side, and then we are moving to the right side, and that will be the MSB. And first we push out the command byte, which consists of 6 bits of address, and then the other 2 is the W, which is in this case we are writing, and then the MB, which is the multi-byte bit. So if the first bit here is set to high, that means that we want to read, and that you can see down here, it's high. And when it's set to low, it means that we want to write to the register. And then the MB means that we want to, in this case, write multiple bits. And here the MB in the read means that we want to read multiple bits. And we have to be able to tell this to the accelerometer. So we have to kind of modify the register address to actually encapsulate these 2 bits in it. And how it's done is that we create a local variable here, and that I will just call command byte. And then what I do is that I take this 0x80 and I use the bitwise OR operator, and then I bitwise OR it together with the register address. And 0x80 looks like this, and that means that on D7 we put a number 1, which means that we want to read from the register. If you remember, right here, this bit is high. So that's what we want. And then we have to take care of the number of bytes as well. And that is done with this. If the number of bytes is larger than 1, so we pass the number which is larger than 1 to this function, Then we further modify this comment byte, and then we use again the logical OR operation, and we OR it together with 0x40. And 0x40 looks like this. I just put a space here so it's easier to read, but you can see that that modifies D6, which is the MB right here. This is D6. And then if this is set to 1, then the accelerometer will know that it has to return multiple bytes. And you will see that this will be very useful when we try to read out the acceleration values of the 3 axes. And with this, you can see that we actually completed this command byte, because we have the address bits already passed to the function. We also made sure that this is set to 1, and we also made sure that this is set to 1 as well. So now we have to do the actual transaction. And for that, similarly to the previous write register operation, we have to pull the chip select low. So GPIO and then write bit, and we are still on the GPIO C, and then pin 4, and then bit reset. So chip select is low now. So then we have to transfer the comment byte, and this will tell the chip what we want. And then we write a for loop which starts from 0 and goes until the number of bytes, step by step. And then what we do here is that we actually fill in the buffer. In each iteration of this for loop, we pass the SPI transfer shifted out with these dummy bits or bytes. So we pass the output of the SPI transfer to the ith item of the buffer. And then this goes until we reach the number of bytes. And then the transaction is done. So we have to set the chip select high. So I just do it like this. So this is the read register. So I press F7 again. And then this is also compiling as it should be. So now we have everything to kind of communicate with the chip. So let's implement a function which initializes the chip. And to initialize the chip, we need a few things. And those few things can be found in the register map. So as you can see, this accelerometer has a bunch of registers. And what we can do here is that we can select which registers we want to work with. And from that, we can look them up and see what we can basically modify in those registers. What we will use here is the device ID register, so that is under the 0x00 address. And then we also have a register which can be found here. So this is the power control 0x2D, and this will be used to put the device into measurement mode. And then we also have another, which is the data format. So this will tell the device that we want to use it in full resolution, and we want to use the SPI with the 4-wire mode. And we also want to tell the range, which can be read here. So the device can go ±2G up to ±16G values. So that's what we want. And then a bit earlier, I jumped over it. We have this BW_rate register. We can select the data rate, and that I will set to the highest one, because why not? So that we have to also figure out. So then let's write a function that we will use to initialize the registers and the chip. So it will look like this. And then we just have to write registers basically here. And then one of the registers is 0x2D. This will be regarding the power settings. And I just have to pass the 0x08 value to it. And that will mean that only the D3 bit will be 1. And that means that we use the device in measurement mode. So it will look like this. And then just to be sure, I wait, let's say 100 milliseconds. And then I do the next line. And this is the data format. And you can see that again, just the D3 is 1, but actually other parameters are also important. If you look at the parameters on the data format registers page, then we can see that, for example, if the D6, the SPI bit was set to 0, then actually we selected 4-wire SPI mode. Then the D3 is set to 1, as I showed, and if the bit is set to 1, then the device is in full resolution mode. Otherwise it would be just 10-bit instead of 13 bits if I would set it to 0. And then D1 and D0 is set to 0 because I just used the lowest range here, so plus minus 2G. Again, I apply some delay here and move on to the next register. And that will be the 0x2C, which is the BW rate. And I just do it like this, which is equivalent to this, which means the highest speed. Here you can see that if I set all the bits to 1, then we will use the 3200 output data rate. And that's what happened here. And then we would like to discover the chip. Actually, this could have been done in the beginning, but I'm fairly confident that my code will work because I have already tested it, of course. So I just show you what we are doing here. So we need a byte variable, and I just call it voice. And then we need to read a register, and that register is the 0x00, if you remember. We want to read 1 byte, and then we pass this to the voice variable. And then we do the following thing. If this is 0xe5, and I show you why it is this value. So here in the register 0, the device ID is 0xe5. So if the device returns this value to us, then it means that we are able to communicate with it. So then, if this value is this, then we do something, otherwise we do something else. And what we do is the following. Here we do a printf, and then we just say that the chip was recognized. And then we can actually pass the number to this. So we can see what number is being sent. And then that will be the voice. And in the opposite case, you can do the same, but just tell that the chip was not recognized. And this compiles, so this is fine. So do it like this, and put it here, and put it here. So now we initialize the SPI, and we initialized the chip itself. So we can actually test this, but before, I want to do my usual printing, so this could be something like this. So I just want to print this on the USART, so we know that something is going on. So one nice thing about this IDE is that it has a nice serial terminal, so let's use that. So in the tools, we have this serial port debug tool. So we can see that the device, which I already connected, is under COM5. So let's open it. And nothing is visible, of course, because I think we missed the message because I have already plugged in the things. So let me restart the device. So I come back here and I make these things wait a bit. Let's say 5 seconds, just for the sake of demonstration. It would work better if it was like this. So I compile this, and then I upload this. And now we are in the terminal here. And as you can see, we got the message back that the chip was recognized 229, which is the 0xe5. And then we get the same message as we printed right here. So now this works. So we can communicate with the chip and we can initialize it. So let's read the acceleration from it. So let's implement a function that reads the acceleration. So it will be this. This won't return anything. It won't do anything like accepting parameters and so on. It will just run in the while loop. So we have to read the register. And what we have to do is that we read from the 0x32, and I will show you soon why. We have to read 6 bytes, and I will tell you soon why, and we will put everything in the buffer. So here you can see that the data x0, x1, y0, y1, and z0, z1 starts from 0x32, and then we have actually 6 bytes here, and that's why we read 6 bytes. And how it works is that since we tell the code that we are going to read 6 bytes, then the MB bit will be set to 1, and then the accelerometer chip will automatically know that after one reading, it has to increment the address and read from the next address and return the data again. And therefore, it will know that it will start with this, and then it will step up 6 bytes up to 0x37 and just output the data. And we can also see how the data is returned. It is returned as x0 first, and then x1, y0, y1, z0, z1. So after receiving these bytes, we also have to put them together into 3 16-bit integers. Just as a reminder, this chip has 13-bit numbers. It returns 13-bit numbers. So actually this 13-bit is split into 2 bytes, and then we have to do some operation to make it into a whole number. So how we do that is that we will need a 16-bit integer, and then I just call it x for the sake of simplicity. And then what we need to do here is the following. We need to cast the whole number into a 16-bit integer just to be sure. So I start with this. And then what we do here is that, again, we need one cast because we take the buffer and we take the 1, which is the second byte we receive, so that will be x1. And this 8-bit number have to be shifted up to the upper part of this 16-bit number. So we do it like this. And then we have to combine this with the buffer 0, which is x0 in this case. And then that's that. So what we do here is that we take the buffer 0 as is, and then we combine it using the bitwise OR operation with the upshifted buffer 1. And then when these two is combined together, then they will be the full number together. And even though it's just a 13-bit number, it has to be stored in a 16-bit variable because that's the closest type that we can use. So then I just copy paste this, and this becomes y, and this becomes z. And then we just increment everything by 2. So this will be this, and this will be this. And here similarly, this will be this, and this will be this. So again, this is now y0, and this is y1, and then z0, z1. And basically this is it. So we have these numbers. And we have to print these somehow. These are now the raw readings of the accelerometer's AD converter, which is not super useful for us because it would be much better if we would be able to represent these numbers in, let's say, G equivalent units. So how many times the G acceleration is experienced by the chip in these 3 axes, that would make more sense for us. But that is represented with floating point numbers. And if you followed this tutorial series from the early times, you could see that doesn't go very easily with these microcontrollers, and we have to use some tricks. So actually I will use some tricks to print the acceleration in G units in floating point numbers. So let's implement a function for it, and since I will call that function in this, just to be sure, I will define it before. So the function won't return anything, but it will accept a parameter, which is the raw data, which is basically one of these conversion values. And then what we have to do is that we need a very large type. So we use an integer on 32 bits. And then let's call this scaled number, because this will be the ADC conversion scaled up to like G values. And what I'm going to do here is that I take the raw number, which is the parameter that we received, I multiply it by 10,000, and I multiply it by 10,000 because I will need 4 digits, and then I divide it with the LSB value, which is 256. And so far so good. So this will be our, let's say, G times 10,000. And then we have to extract the whole part. So I do it like this. And how that is done is that I take the scaled, so the previously like created number from here. So I take this, and then I just simply divide it by 10,000. So this will give us basically the integer part. And since we cast it to integer, it just returns, for example, 1 or 2 or something. And how to get the fraction is the following. So what we do is that we cast again to integer, and then we take the absolute value of the scaled modulo 10,000. So what this operation will do is that it will take this value, and then it takes the modulo of the 10,000. So for example, if the value was, I don't know, 11789, then if I do this with 10,000, that will give us actually 1789. So it basically removes this part, because that's the remainder after 10,000. So then actually, if I would put a dot here, you now get it, that we get the fractional part. But then you can see that here the compiler is kind of complaining, because we need to add the library here at the beginning, because the current library set doesn't have what we need. But now we have this standard library, and there's nothing wrong here. And now comes the cheating. So what we do here is that we do a printf, and then the printf format will be funny. So we put a decimal number here, and then we print a dot, and then we put another decimal with 4 digits, and that's our number. And then the first D there will be the whole part, and then the second is the fractional part. And that's that. So I just press F7 to see if this compiles. And I got some warnings, but it's fine, because they are not used yet. But now I will use it. And I will show you some funny format, and I will explain why I do it. But what I will do is that I print this, and print X without space. And then I print the acceleration G of the X-axis. And then I multiply this like this. So this becomes Y, this becomes Y, and this becomes Z, and this becomes Z. And then I need one more printf, which will print us the line breaks. So the final format will be like X, colon, and the value, and then actually we need a comma here and another comma here. And then we just put this here. And now I compile this, and you can see that the device is spitting a bunch of numbers quite fast. And as you can see, here's the device, and actually you can see how the X, Y, and Z axes are set up. So the Z is pointing upwards, and that's why we get like a nearly 1 value on the Z, and the X and Y are nearly 0 values. And if I tilt the device, then you can see that the other values are changing as well. But why I want to print this way is the following. I close this, and I open the Arduino IDE, and the Arduino IDE has a serial plotter. So I can open this, and we can see the 3 axes. And if you check the top left corner, you can see X, Y, and Z. And Z is green, and that is at 1, because now it's reading 1G. And this is why I wanted to format the output in the specific format that I chose, because now I can plot it in this plotter. So what I can do here is I can resize this a bit, and then hopefully you can see, maybe it's better like this, that the Z is pointing upwards, so it's perpendicular to the surface of the chip, and then the X is let's say from left to right, and the Y is from top down on the plane of the chip. So if I would show you some different rotations, you would see how these 3 numbers transition. And hopefully I won't unplug the device. So I just flip this. Now it's upside down, so you can see that the Z is -1. I put it on its edge, and now you can see that the Y is +1, and if I would put it on its other edge, then you see that the Y is -1, and just similarly I can put this this way, then X is -1, and finally X is +1. So there's the chip. Now I put it back to the default, and there are many things that I haven't shown with this chip. For example, it can detect taps, and how it detects is like exactly this, that if you tap on the chip, there will be a certain like set of waves, and that certain set of waves can be recognized by the chip, and then it can actually trigger one of its interrupt pins, which you can then use as a trigger for some action. For example, you can let your device, your microcontroller, sleep, and then you can wake it up from sleep when this tapping is detected. And you can see that this is very high speed acquisition and plotting as well. So if I would move this in a bit nice way, you can see that, for example, it picks up the vibrations very well. So actually this accelerometer can be, or any accelerometers, can be used for detecting vibrations with different frequencies and stuff. And then you can do very fun signal processing on them. And you can do very interesting projects using them. You can use them for maintenance, you can use them for detecting failures in bearings or whatever moving things, and so on. So now, as you can see, we developed the working code using SPI communication and using this ADXL345 accelerometer. So if you want to get more details, then go to my website. I wrote a nice article about this, and you can read all the details. And also on my GitHub page, I shared the main.c file, so you can just copy paste it and you can use it. As you could see, I used it in the video. And if you like these kind of videos, please consider joining my YouTube channel membership. It helps me a lot, and it allows me to spend more time on these kind of videos where I can show you how to use, for example, these kind of microcontrollers. So I hope that you found this video useful. I hope you learned something, and see you in the next video.